So welcome everyone to today our IEEE distinguished APS lecture, and we are the organizers is our IEEE ISC MTT APS student branch chapter. So we welcome all of you to this distinguished lecture. Today our speaker is Professor Cynthia Furse. She is a fellow of IEEE and the National Academy of Inventors and is a professor of electrical and computer engineering at the University of Utah in USA. Her research interests are the applications of electromagnetics to sensing and communication in complex lossy scattering media, and also like she has several other topics like geophysical prospecting, ionospheric plasma and complex wiring networks, and many others. She is also a founder of a spin-off company, Livewire Innovation Incorporation, and she has taught various subjects. Among them are electromagnetics, wireless communication, etc. She is also an associate editor for the Transaction on Antenna and Propagation, chair of the IEEE Antenna and Propagation Society Awards Committee, and also is past administrative committee member for the IEEE AP Society, and also past chair of the IEEE AP Education Committee. She has also received numerous teaching and research awards. Among them, one of them is 2020 IEEE Chain Toe Tie Distinguished Educator Award. So with all this, I welcome Professor Furse to this lecture. So the floor is yours, madam.
Well, thank you very, very much for inviting me. And you're right, it's night for me, and I see what a beautiful day it is for you in Bangalore. So I'm going to just share my slides now. And like I say, the only trouble is I can either see my slides or I can see you. I can't see both. So if questions come up, please interrupt me.
Yeah, sure.
Okay, cool. So I'm going to talk, I was asked to talk today about the stochastic finite difference time domain method. You'll have to forgive me that this is a bit of a math heavy topic, but I'll try to go gently and show you the significance of the equations, not so much the details of the equations themselves. We started this work because of a really interesting problem, which is the evaluation of fields inside the body. The cell phone example is one of the primary ones. And so if you wanted to know how the specific absorption rate or the power inside the body is changing, you also need to know how that varies with the tissue properties or variation in the model. And so that's what's stochastic about the stochastic FDTD, is what changes and how does that change the fields. I'd like to acknowledge my co-author, Hadia Masumi-Abeshe, who is doing a postdoc in Madison right now. She did this work with me as a young student at the University of Utah, and you can find our papers on emlab.eng.utah.edu. Look in the FDTD section for these papers. We'll be sharing our codes there soon as well. As you mentioned, I'm from the University of Utah. I thought you might like to see where that is. Here's a map of the United States, and Utah is in red, and then the little star is where University of Utah is. We are right in the middle of the Rocky Mountains. It's very beautiful. It's a lovely time of year. We've just started fall. The leaves are starting to change their colors. Electrical and computer engineering is one of the very strong departments at the University of Utah. So again, why did we want to look at stochastic FDTD? These pictures right here are from some work that we did way back in 1996. It was the power deposition in the human head from a cellular telephone. And in all of these cases, we assumed that the tissue properties were exactly known. The size of the model was exactly known. And as a result, the fields could also be exactly known. But we know that's not reality. We know that there's variation in head size, shape, and ear thickness, the location and position of the phone, and the tissue properties, the dielectric properties of the tissues, and all of those affect the specific absorption rate. That's been shown in numerous other publications.
Professor, sorry to disturb. Are you still on slide number 1?
No, I'm on slide number 3. Did it not move?
No, we are still seeing slide number 1.
Ah, dear, that's a bit of a problem. Let's see what I can do to, let me try stop sharing. And then let me see if it will. Let's see if this will be better, but thank you for interrupting me. That would be terrible. Can you see slide number 3 now?
it is, the PPT is still not visible to us. Maybe, yeah, now we can see it. Thank you.
Okay. Red, green, and blue lines?
Yeah, the plots I can see. Yeah.
Okay, let me just go back then and show you again where the University of Utah is. Are you seeing my maps?
Yeah, I can see it.
Okay.
Yeah, very beautiful campus.
Yeah, beautiful campus in the middle of the Rocky Mountains. And again, what we're looking at is the variation in the properties. Now, here's another example of why variation is so important. When you design an antenna for application inside or on the body, you get huge shifts or detuning if you evaluate the different properties of the body. So just little bits of change in electrical properties will completely detune your antenna. So it's really important to consider that as well. Now, SAR is specific absorption rate. There are international guidelines for all of these. I believe that India is under the European Senelec guidelines. We consider in this case a 1 gram SAR, which is about the size of about the size of the tip of my little finger, and the SAR needs to be less than 1.6 watts per kilogram. In the European model, you've got something about the size of my thumb, and that SAR has to be less than 2 watts per kilogram. Either way, you're looking at some very small areas in the body and trying to make decisions about if a phone or other medical device is considered safe or if it is not. So it's really important to be able to evaluate these accurately. Now, the question is, what about the variance? And in fact, that's required in the FCC guidelines. It's not yet required in the Senelec guidelines, although it's likely that it soon will be. So in this case, you have to be able to evaluate the variation in your model, whether you are measuring or whether you are simulating, to be able to say, if you're saying that the 1 gram SAR is less than 1.6 watts per kilogram, it means like how much variation is that? And that all has to be taken into consideration. It's called the variation budget to be able to figure out how much error or variance you might expect in your model. So it's really important to be able to calculate that. Well, there is a very good way of calculating that, and that's Monte Carlo. And in Monte Carlo, you do lots of inputs. You basically make all the different tissue properties, and you put all of those different ones in, and you do lots of test runs. And that gives you a statistical output, and you average all of those to get the mean, and you find the variance or standard deviation from that as well. So that's really awesome, except that lots of these test runs can take hours or days of simulation time. And so in practical applications, that's really limiting. And if you want to be able to do larger applications, in some cases, it's nearly impossible. So Monte Carlo is an excellent method. In fact, we consider it the gold standard. Monte Carlo is the most accurate way that we could be doing this. However, the amount of time is unreasonable and not practical. So we developed this method called the Stochastic FDTD method, or SFDTD. It's based on the finite difference time domain method, which would normally be used to calculate the fields inside bodies. And what this one does, instead of just having an input, it has the input and the variance of that input. So for example, you put in the tissue properties and their variance. You do one test run, not the many of Monte Carlo, and that gives you a statistical output of mean and variance. So here's an example of 3 of the tissues. All the tissues in the body have variation as well. So muscle, fat, and skin are kind of 3 of the most extreme tissues in the body. You can see that muscle is very conductive. If you look at the conductivity, it's 0.87 compared to fat, which is 0.21, and skin, which is 0.43. It's a higher dielectric than the others as well. The epsilon R is 55 compared to about 16 and 39. And then you can also see there is pretty substantial standard deviation in all of these, roughly 10% standard deviation in all cases. In addition, kind of look at the thickness. Muscle is very thick, fat's relatively thick too, skin is pretty thin. So Camelia Gabriel and her team have measured these properties and then provided both the means, which were originally given, and now also the standard deviations are provided for all of the tissues. More measurements are probably needed in order to really make this super strong, but it's important to know these are pretty big variations. So in a regular FDTD, in a regular FDTD example, what you would do is you would use an electric field source. You'd find the mean field, you do some boundary conditions, you'd find the mean magnetic field, and then when it was converged, you would stop. So that's what a typical finite difference time domain method would look like. You basically run that as a function of time. It's kind of like making a movie of your fields, and then in the end you look that it's converged, and you can find your peak values from that. But so here's a traditional FDTD and the kinds of equations that we end up with. This is just a 1D example. Of course, we are doing a 3D case, but it's much easier to show the 1D equations here. So you're going to use Maxwell's equations. They are vectorized, of course, and you convert the derivatives. You can see the partial derivatives in x and z here, for instance. You convert those derivatives into differences. So the derivative in space, the d by dz, is converted to a difference in space, and the time derivative is also converted to a difference in time. So that's traditional FDTD, standard FDTD, and in fact, that's what we're going to do here as well. Well, in this case, for stochastic FDTD, our input is going to be the mean and standard deviation of the tissue properties, epsilon and sigma. Notice I put a little hat over the sigma because sigma also represents variance in stochastic relationships. And then we're going to do one run. So in this case, the way it's going to work is, see, here's the regular FDTD just in white, and then we've added these 3 additional steps. So we do start with an electric field source. That would, for instance, be where the voltage goes into the antenna of the phone. We find the mean value, boundary conditions, mean magnetic field, but then we also find the standard deviation of the electric field. We do a boundary on the standard deviation of the electric field, and then we find the standard deviation of the magnetic field, and then we run that loop as many times as we need to until it is converged. So our FDTD equations are roughly double what they were before. So our single test run, is going to take just about double the original time, but that's a whole lot more efficient than the hundreds and thousands of Monte Carlo runs. So the white again was traditional FDTD, and then we've just added these basic steps. So this is what a 3-dimensional SFDTD mean field might look like. So here's the one for EX. Now, in this case, if you're familiar with FDTD, you can see on the left-hand side, we have an electric field. On the right-hand side, we have an electric field with a set of constants multiplying it. Very simple there. We have some differences of the magnetic field, which came from the derivatives turning into differences. Here's one in space. Here's the other in space. And we have some similar electric equations over here. Now, this is the mean field equation, and these are exactly the same for FDTD and for the stochastic FDTD. We have the conductivity right here. I kind of highlighted the tissue properties where you have epsilon and where you have sigma. And so you can see that the tissue properties are playing into these equations strongly. Now, in the case of 3D equations, we have 6 of these. I'm not going to show you all 6, but we have 6 of these equations. They're all very similar in structure. So we start with a regular, but now if we want to derive the variance equations, the mean equations are the same, but let's talk about the variance equations. So we start with a regular FDTD equation and we expand it using variable equations. So being able to use stochastic equations where we have 2 variables that vary stochastically x and y. Those would be the electric and magnetic fields, for example. And you'll notice that if you wanted to find the variance, which is this sigma squared, of these 2 variables, you would end up with basically constants, and again, of the variance. And then you'd end up with a covariance between them. The covariance term is the term that we're going to end up approximating. So this is an approximate method. So we can exactly consider the variances, but the covariance is going to have to be evaluated approximately. From this equation, we complete the square, we take the square root, and we apply something called the delta method for our inseparable terms, which basically just breaks them apart and then allows us to do an approximation. We end up with an equation like this. So again, forgive me, I know it's a bunch of math, but what I want to show you is the important feature here is we have these same constants that we did before. There's a constant that you'd be familiar with, here's a constant, but we also have this correlation coefficient that comes from the covariance equation. The correlation between 2 of our values goes between a minimum of -1 and a maximum of 1. And you can see them here in yellow. So here, for example, is the correlation coefficient between the dielectric constant and the electric field. Between the conductivity and the electric field is in blue. The one down here is the same as above. And then the pink one is between the conductivity and the magnetic field. So we have these 3 correlation coefficients that we're going to approximate in our application. And then everything else is really straightforward. It's very similar to the kind of equation we have for a regular FDTD, and it runs again just as a function of time. So the important thing here is that we have this correlation coefficient that comes from the covariance, and it's going to have to be approximated. And we know it has these limits, -1 to +1. So actually, and if we had a value of 1, it would mean that these two were completely exactly correlated. If we had -1, it means they are anti-correlated. And if it's 0, that would mean that there was no correlation at all. So then there's another thing that we're going to have to do, and that's calculating specific absorption rate when we are finished. So we're basically going to run that FDTD equation. We're going to run it and run it and run it as a function of time until it has converged. And then we're going to calculate the specific absorption rate. So if we want to consider the mean specific absorption rate, that is going to be the conductivity times the mean electric field squared over twice, and then this rho is the density, standard equation for specific absorption rate. But that is a really important thing. It's power per unit mass of tissue. And again, here's the mean value. Now, the important thing here, and we actually made a mistake in the first FDTD paper that we did when we were getting SAR. We first, let me see if I wrote it here. Nope. Yeah. So the mean of the standard deviation, the magnitude of the standard deviation is not equal to the standard deviation of the magnitude. So what we have to do is we have to let the electric field reach steady state. We then calculate its magnitude, and we do that using a 2 equations, 2 unknowns method. And from that, we're going to be able to calculate the specific absorption rate. So the electric field shown here as a sine wave, let's say that we ran a single frequency sine wave. In order to find its peak, we could wait for the peak to happen and then just like look for a maximum value. That's been done in FDTD. But the most accurate way is actually to use the assumption that this is a sine wave. You put in a sine wave, you're going to get out a sine wave just from the linearity of electromagnetic equations. So let's assume that we have Q1 and Q2, which are 2 points on our sine wave at times T1 and T2. We know that those are the magnitude of the electric field times the sine of omega. We know omega because we put it in, these 2 time values, and then the phase. What we don't know is the magnitude and the phase, so we need 2 equations. That's the 2 equations for our 2 unknowns. Our 2 unknowns are magnitude and phase. You can solve these for the magnitude and the phase directly, and so you only need to be able to have 2 points, and they don't even have to be far from each other. You just need to have 2 points on the sine wave that aren't both 0, and that will allow you to calculate the magnitude and phase. So we can do that for the electric field. We can also do that for the specific absorption rate. So in this case, we know that the magnitude of the electric field is its mean value plus its standard deviation. So if we wanted to calculate its standard deviation, we're going to take its magnitude minus its average value. And that's what we do. So the variance of this, we can calculate, again, using the equations that I showed you before. And you can see that we've got our mean value of electric field. That's easy. That comes from our regular FDTD. We've got our variance, or our standard deviation, which is the square root of the variance. That's easy to get as well, because we're going to get that from running the stochastic FDTD. And then in the yellow, we have this correlation coefficient. So this is relatively straightforward to calculate once we've completed our FDTD simulations. But we do need the magnitude of the electric field, and that comes from our 2 equations, 2 unknowns. Okay, so those are the basic equations. Now let's see what we can do with them. So here's the University of Utah 3D head model. The reason we chose this model was because I wanted to be able to compare exactly to the work that we had done previously. So let's consider, and okay, there's one other reason. I didn't want to implicate any commercial phone. I didn't want to run a specific phone from a specific company. So we evaluated a half-wave dipole. We put in a 1 volt per meter sine wave, and we considered 835 megahertz, which is on the very low end of the cellular telephone bands. And then we put a perfectly matched layer around the outside. That was our boundary condition. And we evaluated our mean and standard deviation. So here's our mean and standard deviation. Just look left to right. The SFDTD was done with 1 simulation. The Monte Carlo was done with 1,000 simulations. These are very nearly identical. So visually, they look pretty identical. And you'll see in a minute that numerically they are as well. So the mean SARs, those are dead on. That's very, very, very close. Again, here's the mean SAR looking kind of at a different angle. And finally, the last angle. So our mean SAR's really, really close. Monte Carlo took 1,000 simulations, and it did take nearly 1,000 before it converged. And in fact, it's probably even not perfectly converged at that point. And the SFDTD took 1 simulation. Now let's look at the standard deviation. And remember I told you that SFDTD is approximating the standard deviation. So we can assume that the Monte Carlo standard deviation is the most accurate, although even though we ran 1,000 simulations, it still had a little bit more converging to do. If you glance at these two, you can see that they are very close, but not identical. So they're very close, but not exactly the same. And here's a different cut. Again, very close, but not identical. And finally, right here, very close, but not identical. So our standard deviation is an approximation. In these three that I just showed you, the correlation coefficient is its maximum value of 1. Now let's convert it to it so that it has a maximum value of 1/2 and see what the difference is. So the top picture has the correlation coefficient of 1. The bottom picture has the correlation coefficient of 1/2. And then you see Monte Carlo as well. There is a little bit of difference in this case. And in fact, in our example, the correlation coefficient of 1/2 was actually closer to the Monte Carlo than a correlation coefficient of 1. Again, let's do some other cuts through the head. And finally, one last cut. So again, the correlation coefficient of 1/2 was closer to the Monte Carlo values. So that's what we would use again in the future. Now let's look at the mean SAR. I mentioned that Monte Carlo and SFDTD are really, really, really close. This is actually pretty interesting because a lot of times people assume that their regular FDTD is absolutely perfect in the mean value, but the truth is Monte Carlo really ought to be better, but maybe it's not quite converged, but they're very, very close, very close. I'm looking at all the different tissues that we have in the head. The cartilage, which is where the ear is, has the highest value, followed by skin, none of that's surprising. And then the pineal gland, pituitary gland, and brain are going to be next closest. Cerebral spinal fluid is this CSF. You're going to see that's pretty high as well. So even for the high values, the mean values are really close. Now here's the standard deviation, and I'm showing you the standard deviation of Monte Carlo in yellow. That's the gold standard. So consider that one to be the most accurate. And then I'm considering SFDTD with a row of 1, a correlation coefficient of 1, which probably overestimates the standard deviation, and then a row of 0.5, which was closer as we see. So if we were to look at the highest value right here, which is cartilage, we can in fact see that SFDTD was slightly overestimating the standard deviation, and that it's closer when we use a row of 0.5 versus 1. Now, in all of the areas that we have the highest values, so cartilage and skin, for example, you're seeing this trend. When you get over to the pineal gland, pituitary gland, and brain, the SFDTD actually underestimated the standard deviation. We aren't sure if it's the SFDTD underestimating or perhaps the Monte Carlo is also a little bit overestimating, because even at 1,000 runs, it wasn't quite complete. And this took us, I can't remember, it was nearly 2 weeks to just be able to run this. Okay, so let's go to the next. And I just want to be able to compare the mean and these standard deviations, because that's pretty important. So we know that SFDTD is giving us a pretty good representation of the standard deviations, but let's just look at how those relate to the means. So if we were to consider cartilage, we can see that the standard deviation, which is, so here's the mean, which is in red and blue, and here's our standard deviation. Our standard deviation is nearly half, 30 to 50% of the mean value. That's huge. That's a very large standard deviation. So just from about a 10% variation in our tissue properties, we end up with a 30 to 50% variation in the mean. And that's really significant. We see that for all of these tissues, that our standard deviations are pretty significant. So that definitely means we have to consider those when we're doing our electromagnetic simulations. Now let's go to the 1 gram and 10 gram SAR values. These are what are actually used in the guidelines that are used to decide, for example, if a cell phone can be sold. So here is SAR for 1 gram and 10 grams if you compare Monte Carlo and SFDTD right here. And you can see that your 1 gram SAR and your 10 gram SAR are really close. So the mean values, very, very close. If we consider the standard deviation with two different values for the correlation coefficient 1 and 0.5, you can see that we are overestimating, in this case, the 1 gram and 10 gram variance, and that's okay. So we would rather overestimate our variance than underestimate our variance in this case. So at least the SFDTD, when it is an approximation, is an overestimate of the dominant values as opposed to an underestimate. So that's really good. Now, we also wanted to be sure that we were getting the location of the 1 gram and 10 gram SAR, and we are. We're within just a cell or two, and these are a millimeter or two. We're within a millimeter or two of exactly the correct location that are shown here in these dots. So not surprisingly, we did get a really good location on those. And then here's an example of the simulation time. So we actually evaluated this at 835 megahertz, where I showed you the data at 1900 megahertz. We've calculated that as well. That's in one of the papers if you want to go and see those pictures too. And you can see that the simulation time between like the 835 megahertz, which is the smallest of the models, SFDTD took 996 seconds, whereas Monte Carlo was taking over 475,000 seconds. When we did the 1900, that model has to be larger because it's a higher frequency, so the cells have to be smaller. They have to be twice as big. SFDTD, you have to square that value, ends up being about 20,000 seconds, and we couldn't even run the Monte Carlo for the 1900 case for comparison. So that's very significant. So our conclusion was that there is a very substantial variance in SAR, that our SFDTD slightly overestimates that variance, which we consider good. And so if we were to consider how much variation there was in this case, how much variance, we would say it's 1.6 plus and minus 0.7 watts per kilogram, and similarly for the 10 gram plus and minus 0.6. So this definitely indicates that the SAR guidelines should take into account the expected variation of SAR, and frankly, really all of our electromagnetic calculations, we need to be considering that. So again, I mentioned that we have this website, emlab.eng.utah.edu, that includes the papers. And now I'm going to go on to the next piece of this. And so I just talked about what would happen if you changed the dielectric properties. Let's look at what would happen if you had just little changes in your model. So that is a geometrically stochastic FDTD method, and for, again, the same purpose. So remember we said, why would we do this? It's because the head size, shape, and ear thickness change, as well as the location and position of a phone and the tissue properties. The bottom one is what the SFDTD method takes care of, and the others, which are all geometric, head size, shape, etc., those can be taken care of with a geometric stochastic FDTD method. Well, a geometric SFDTD method is very similar to a just regular SFDTD method, but the variance that we're putting in, instead of being tissue properties, is our cell size, dx, dy, and dz. Again, we're still going to do one test run. So we use these same variables. We assume that we have a multivariable stochastic function, and we use this delta method to approximate that. We treat it as a summation, and we just terminate our summation depending on how accurate we need it to be. So I'm going to show you some results from a 1D simulation, just so you can get some idea kind of, where we're starting, and then we'll go to 3D from there. So you'd have air, skin, fat, and muscle. And each of these could have some variation in their tissue properties, that would be SFDTD, but also in their thickness. So skin is pretty thick. It's on the order of 5 millimeters. Fat's about 54 millimeters. And then muscle, in this case, we're assuming is 42 millimeters. And we use these average FDTD equations. Those are exactly the same. No changes from our regular FDTD equations when we're doing the mean. But when we do the standard deviation, same thing. But notice that we have these variances of delta Z shown in the blue. So that's what we're going to assume for variance in direction. And then again, we have these correlation coefficients that are going to have to be approximated. In our previous case, the correlation coefficients were between the tissue properties and the fields. In this case, the correlation coefficients are between the cell size and the field in each case. We also have to adjust our Courant stability limit. So anyone who's done FDTD knows that you have to limit your cell, your time step, in order to basically not jump over a cell before the field gets there. So we have to include this variation in our Courant stability criteria. So we just use the worst case for there. We make sure that we are using a time step that is optimal for that. So again, we do the same thing that we did before, our GS FDTD, same thing, except we're using our regular FDTD equations. We start with an E field source, we get the mean field, mean electric field, we do the boundary conditions on that mean field, and we get the mean magnetic field. Then we get the standard deviation of the electric field, we do boundary conditions on the standard deviation, and then we get the standard deviation of the magnetic field, and we just keep that going in a time loop until it's converged. So for our 3-layer model, we're actually going to use a ramped sine wave with 1 volt per meter. We're going to use a 2 gigahertz model and a spatial resolution of the minimum lambda divided by 40. We're going to use mirror boundary conditions on the back ends, and that's just about perfect for a 1D case. So here are our mean values, and in blue and green, that's the mean value for Monte Carlo and the geometrically stochastic FDTD methods. So you can see that those are virtually identical. And then we also have the standard deviations here, which are really, really close. Now, this is assuming that cell size can vary plus and minus 10%. So that's, in our case, say a 10% ear distribution, normal distribution on the ear. If you go much beyond 30%, we could have gone as high as 30%, you start getting instabilities. So this doesn't work for doing huge variations. This is good for doing small geometric variations. Huge variations, you're basically going to have to run a bunch of different models and do Monte Carlo. I don't know another way to get around that. So you can see that, again, our standard deviation is really high. It is, in this case, nearly as high as the mean value. So pretty important here. Here are, this is another 3-layer tissue model, and you can see what happens when we start getting into the skin. In this case, we were looking in detail at the skin-fat interface, and when we look at GS FDTD, it is slightly overestimating the variance in this case. Now let's consider a 2-dimensional example. So this is going to be a cylinder with skin and fat on the outside and muscle in the middle. And I just want you to have kind of a visual picture of how close these really are. So these are the mean values on the left and the standard deviation values on the right, meaning the standard deviation. And you can see Monte Carlo on the top and GS FDTD on the bottom. The mean values are virtually indistinguishable. The variance values are pretty close in this case as well. Next. And then here are steady state phases. So in this case, it was the magnitude, but because phase is also important in these cases, let's look at the phase as well. So right here, you can see that the steady state phase is a little bit different. There is a little bit of delay between the GS FDTD phase and the Monte Carlo phase. So a little bit of change there. That was pretty interesting when we saw that. Now let's consider a 2-dimensional human head model. And what we're going to change here, so this is just cross-section through the head, the nose is on the bottom, the ears are on the left and the right. And the yellow area is the skin fat region, and that's what we're going to be changing. So we allow the skin and fat thickness to vary by plus and minus 10%. We put this 1 volt per meter sinusoidal wave on it. And then you can see the mean and the standard deviation on the left and the right. In this case, the standard deviation is about 1/10 of the mean value. So it is smaller than when we have the tissue properties, which is, I guess, encouraging, interesting, whatever. You can see that you get a lot more variation, of course, on the side where you have the phone, but notice what's also happening on the nose and into the sinuses, kind of on the bottom of this picture. Pretty just interesting. You end up with quite a lot of variation at the tip of the nose. I'm not sure if anyone cares about the tip of the nose more than they do the brain, but once it starts getting into the sinuses, people care a lot. That's an area that we consider to be medically significant. So the mean and standard deviation were calculated. This is showing you the GS FDTD on the top and the Monte Carlo on the bottom. And again, notice the variation. The mean is virtually identical. The variation is very, very close in this case. So here is an example of the mean and the standard deviations from our geometrically stochastic variability. The two blue ones are the mean of the GS and the mean of the Monte Carlo. Notice those are identical. And then we have the standard deviations that are very close. But notice that again, in this case, the standard deviations are so much smaller than the mean. So the effect of the skin and fat thickness was having a much smaller effect than the effect of the dielectric property changes. So that was interesting. Just blowing up, making these bigger so that you can see the relationship just for the standard deviation of the geometrically stochastic FDTD, which is dark red, and Monte Carlo, which is blue, which is not blue, which is kind of pinker. Again, we are overestimating the variance by a little bit with the geometrically stochastic FDTD method. So our future work is to combine the geometrically stochastic FDTD with the stochastic FDTD and put it into a 3D human model. Part of our thought about this is we can do this, but I don't think I can run enough Monte Carlo simulations to actually be able to evaluate this. So we haven't actually completed this work because I can't actually do a Monte Carlo method to compare it to. So it's definitely a useful feature, but without being able to compare to Monte Carlo, we haven't moved that forward. So now I would love to answer any questions. And again, let me just remind you, if you're interested in picking up any of these papers, they're at emlab.eng.utah.edu. And I've put my email there, but I'm actually going to switch over to being able to see the Zoom. So hopefully I can answer some of your questions. Just drop over to that instead. Okay, so like I say, I know I know that it's a little bit hard with all of the equations, but I hope that I was able to just make it so you could understand them a bit. What questions do you have about this movie?
So, Professor, yeah, thank you for the talk. So we did not get any question yet. Maybe people can write it down now. Yeah.
And please don't be afraid of asking questions. There should be questions from this. Okay, so Kieran is asking a really interesting question. When the number of random variables in the problem is increasing, how does the complexity increase? Well, exponentially, basically. So in the case of stochastic FDTD, you can have all of the tissues vary. That doesn't increase the complexity at all. So all the tissue properties could vary. They could even vary from point to point. Like if you wanted to say the left side of the head has more variation than the right side of the head, you could do that without increasing the complexity. However, as soon as you have different variables such as tissue properties and geometry changing, now that does actually increase the complexity. So yes, as you increase the number of random variables, the complexity of the equations, I mean, the types of random variables, the complexity could increase. However, it's still going to be less than Monte Carlo, because as you increase the Monte Carlo, I think it goes up by n squared. It goes up tremendously, and you have to run it so much longer, so many more time steps. So yeah, it's really hard to do combinations of more and more random variables. AntKit has put in a really good question, which is what are the boundary conditions that are used during the simulation? So in most of our cases, we have chosen to go with just the Muir boundary condition because it is much simpler to program than any of the others. The other boundary conditions could be programmed as well, such as the PML, perfectly matched layer. But for bioelectromagnetic simulations, the Muir boundary conditions are actually really good. And one of the reasons for that is that the body absorbs so much of this energy that even when if you were to get reflections coming back, it absorbs everything. So it's really nice to be able to just use a simple boundary condition like Muir. Now, when you do a regular FDTD simulation, you put these Muir boundaries around. They're very inexpensive boundaries. That's great. However, when you do the stochastic FDTD, remember that you are calculating not only the electric field and the magnetic field, but their standard deviations. And so you have to have a boundary condition for the standard deviation also. In regular FDTD, we have a boundary condition for E, but we don't need one for H, just the way the cells are aligned. And the same thing applies when we do the stochastic methods. So we need to have a boundary condition on the variance of the electric field, but we don't need one for the magnetic field. So we're using mere boundary conditions, and we're using them on both the mean and standard deviation of the electric field, but not on the magnetic fields. We have tried to program these with, or we've evaluated what it takes to program them with other methods. Not too bad, but we've just been using mirror. Ian is asking, is there a suggestion on how the geometric stochastic FDTD could be applied on an unstructured mesh? That's a really interesting question as well. So if you were to have a mesh that was like variable, which would allow you to have much better variation in the shapes of things, you could apply the geometrically stochastic FDTD to those cell sizes changing as well. So even though you have an unstructured mesh, you still have a cell size at each point. So the GS is actually being applied at each point, and the calculation is being done effectively at each point, just using the nearest neighbors on either side. So I think it should apply just as well on an unstructured mesh. You're going to run into some interesting problems when you get to the boundary condition, but even that should be manageable. And I think that there is strong potential for having instability if the structure of the mesh is not, I mean, if it expands too quickly, then you're going to end up with instabilities. We see that in all kinds of FDTD, and we probably see it even worse in geometrically stochastic FDTD. So if your mesh expands too quickly, it's going to go time unstable, it's going to blow up. Okay, so Hamamanth has put in a really interesting question too. How do you decide if the Monte Carlo or the SFDTD is overestimated? Man, that's a good question. So honestly, when we were first doing Monte Carlo just for like 1D or 2D meshes, it was really easy because I could run the Monte Carlo for 10,000 steps. We could watch its how it was becoming stable in all of our points that we were interested in. So we could really monitor the Monte Carlo, and in many cases we didn't have to go beyond a few hundred steps. But that was because we had a very simple one-dimensional model or a very coarse two-dimensional model. As soon as we went to the three-dimensional model and monitored the Monte Carlo convergence, it was pretty marginal, even at 1,000 steps. So I'm going to say that my Monte Carlo, I still trust the most, but it was barely converged. It wasn't extra converged. So then when we look at the SFDTD, and we just looked, did it have a, what was its standard deviation? Since I was trusting the Monte Carlo, SFDTD was slightly more. Now there's also a reason that I would expect SFDTD to have a higher correlation. Particularly when I use a correlation coefficient of 1, I know that I am overestimating the correlation, and therefore, if you just look at the equations, that always is added; it's never subtracted. So I know that I would always overestimate the variance of the SFDTD. So I would mathematically expect that my variance would be overestimated if my correlation coefficient is overestimated, and I know that 1 is an overestimate. Now 0.5, I don't know if that's an overestimate or not. I kind of do, because when we were running our two-dimensional cases, we would actually calculate the correlation coefficient, and 0.5 was still an overestimate. And again, we saw that it did overestimate. So with a correlation coefficient of 1, you can guarantee that SFDTD is going to get or overestimate the variance. With correlation smaller than that, it could be more accurate, but you may at some point not overestimate the variance. Tazeen asked, have I considered just a minute, I lost that one. Have I considered anisotropic permittivity in any of these simulations, or isotropy, or is isotropy a good approximation? That's a good question as well. So for human tissues, we do have a couple that have really strong anisotropy, and that is the long bones in the leg and the long bones in the arm, where the cells are really elongated. And in those cases, you have much more conductivity in the long direction than you do in the short direction. But for the head, isotropy is a really good approximation. So our skull, for example, doesn't have really long long tissues, they tend to be more moderate in their growth. So we just really don't have a lot of anisotropy in the head at these frequencies. There could be other frequencies where that isn't applying, but at the cell phone frequencies, isotropy is a really good model. And again, if I go to other parts of the body, that may not be as good a simulation. Now, how would anisotropy play into this? I don't think we'd have any trouble with it. So the stochastic FDTD wouldn't even change. The regular FDTD equations, of course, would have to be the anisotropy equations, but the stochastic version of that would be the same. And then if we got to the geometric ones, we consider the variance of dx, dy, and dz separately. So we could easily have included that as an anisotropic example. So good question. It wouldn't change our process. And for the head, it's not important, but it could be in other applications. Saha is asking, actually, Abrupa, do you think of translating to optical devices based on imaging for separating similar tissue properties? Optical devices have definitely been simulated with FDTD. We haven't simulated any optics with stochastic values, but it's really interesting that you could. Could I use optical devices to image and therefore measure the tissue properties? That's a good thought. Their frequencies usually aren't quite right for this application, although they are for other devices. So our measurements do need to be improved. We just have one set of measurements telling us approximate variation. And so our conclusion is not so much, that's why I didn't want to simulate a specific phone. I can't give you an exact number for what that variance would be because the measurements are still, it's just one set of measurements. We need more. Nijendra asked if a covariance of 0.5 was close, it was closer to the Monte Carlo. Yeah. Would it be different with a different problem? And how do I take care of that without comparing with a Monte Carlo simulation? Good question. So it is true. The covariance, the correlation coefficient of 0.5 was closer to the Monte Carlo. In fact, I think if I dropped it to 0.35, I was even closer. Would it be different with different problems? Yes. It's interesting. We checked in all of our cases, like in our 1D cases when we made it coarser and then we got more and more fine. The covariance value still stayed about the same, because you can actually calculate if you run it with Monte Carlo, you can actually calculate what the covariance should be. But by then you've run the Monte Carlo, there's no point in running anything else. So yes, it will be different with different problems, but it didn't seem to depend on our resolution. So if I had simulated a cell phone next to the head at 835 versus, a hyperthermia application, yes, I could expect a different correlation. And then how do I take care of that without comparing with Monte Carlo? If I want to be sure that I am overestimating and not underestimating my variance, such as if it's for a legal thing like certifying a cell phone, I'm just going to use a correlation coefficient of 1. And I'm just going to know that I'm overestimating my variance, and I'm just going to see if that's important or not. So really, I just want to know if the magnitude of my variance is going to be important, and I'll definitely be able to tell that with a correlation coefficient of 1. Kieran is asking if rectilinear grids in FDTD faithfully represent the complex geometry of biomodels. Oh, good question. And is there a mathematical way of comparing the Monte Carlo and SFDTD, or is it just a visual comparison? Okay, so first of all, rectilinear grids and the complex geometry, let's say, of the head. So anytime you're doing an electromagnetic simulation, such as this, you want to know that the model you're simulating is giving you the results that you get. So if I had a head that actually had these little, stair steps, the results that I got would actually be what you see in our FDTD simulation. And then you have to ask, and this is a theoretical question, if I had smoothed that, would I have ended up with different results? And the answer is yes sometimes and no other times. In the case of these biomodels, the answer is generally it doesn't have any effect. The time that you would have an effect is if you're going to get a surface wave. Now, in all of our cell phone applications, you do not end up with surface waves. The waves go in, they either reflect or they are absorbed. They don't get going around the surface. There are other frequencies. There are higher conductivities that can make these surface waves happen. But these types of applications with the head and the body at these frequencies, we don't see those surface waves. If you have surface waves, the rough edges really matter. And in that case, no, it would not be a good enough representation. But in these, because we don't get surface waves, yes, the rectilinear grid is actually a very good representation. Now, you also have to ask about the resolution of that grid. And even if you have like a lambda by 40 or even lambda by 100 or more, that may or may not have enough resolution for the size of the thing you're simulating. So, for example, if I really wanted to know about the pineal gland, I would go with an even finer grid. But yeah, the rectilinear grids are pretty good here. But there are other applications where they're not. And then, is there a mathematical way of comparing the Monte Carlo and the SFDTD? And the answer is yes. And actually, if you go to our papers, we did as well. For me, the first and most important thing was actually the visual, because I needed to know that the shape, the locations, because those are really important in this application, that the shapes and the locations and the magnitudes were all pretty close. Then if you want to actually compare them, you have to kind of compare them either magnitude to magnitude or phase to phase. And yes, we found that the magnitudes were really tight, but there is some shift in the phase. So you'll find that stuff a bit in our papers. The Genders reminding everybody to fill out the feedback form. And then someone else has said, have we missed lecture? Yep, it's being recorded. One more question here is, when to choose SFDTD over FDTD for biological and non-biological applications? So SFDTD is important anytime that variation is important. FDTD is just you assume mean values and it gives you mean values. I'm going to argue, and this is a very debatable statement I'm going to make, but I'm going to say that for virtually all of our bioelectromagnetic applications, it's going to be important to consider the stochastics. And the example I will use is, so of course this one, certainly, we're looking at SAR, we might be looking at certifying a cell phone, but imagine we're designing an antenna. I design antennas that go on pacemakers inside the body. And if I have even small variations in the tissue properties, it detunes those antennas and makes them not work. And therefore, it would be important to consider the stochastics of that so that I could design an antenna that was less sensitive to the variability of the body and be able to consider that one. So SFDTD, I'm going to argue, and I am going to, like I say, this is debatable, but I'm going to say it's important in all bioelectromagnetic applications. And will the boundary conditions change or remain the same? The SFDTD boundary conditions have to be added. We have to have a stochastic boundary condition as well. Thank you so much for all those questions. I love your questions. Oh, one last. Okay, let's see. Got to see more. I am assuming Gaussian random variables, so a normally distributed random variables. And if so, would I be able to handle the minus v values of the permittivity coming out of random realizations? The answer is no. So I am considering a Gaussian random variable. Is that actually accurate? Our measurements are saying, well, close, but not identical. So if you do not have a normal random variable, then you have to go and do a different stochastic approximation. But the one that we've made is for a Gaussian random variable. Best I can do today. So thanks very much for your questions. Again, I'm going to mention that we should soon be able to share the codes on that same website that I gave you if you want to end up playing with this method too.
Oh, okay. So yeah, thank you everyone for asking question, and obviously thank you, Professor, even though very late at night delivering the talk, and you still finished on the same day. I can see on your screen that
Yes.
5 minutes till next day.
Yeah.
Yeah. Okay. So okay, Professor. Bye then. Yeah. See you next time. Yeah. Bye. Thank you everyone.
Everybody.
Bye.
Have a great day.
Yeah. You too. Good night.
Okay. Bye-bye.